What is up, winning team? And hello and welcome back. We're continuing our current book series, Beyond the Veil, Exploring the Bubble Theory and the Fourth Dimension by Jamil Chamberlain. Guys, going by the book in the description box. It's really good. It's super cheap and you can read along with us. I am plugging it because it is the husband of my friend. And so I'm very proud. You guys know this is the winning team, right? What we do at the winning team is we support each other. So I'm so excited to be able to read a book by somebody that I know. And as you guys know, we're doing the dimensions of the universe. I've been telling you guys that I want to know about the dimensions to start to delve more into the dimensions. And this just feels like the right place to be because we're doing the fourth dimension and the bubble theory, which is going to be explained in this. So I won't speak for him. We will read. We're starting in chapter 3 today. If this is the first of the videos you're watching, go and check the other ones out. They will be linked in the description box below, alongside a link to get the book for yourself. But yeah, we'll just get straight into it. You can watch the other videos, the intros, whatever's to get to I know why we're doing this more. But I told you guys my next scientific deep dive is going to be the dimensions of the universe. So I thought, let's read along together. Let's work together, right? Okay. So we're in chapter 3, the building blocks of the universe. Atoms, the invisible architecture. You guys know I love me some atoms. Obviously, I'm a chemist technically. That's my area of science I specialize in. So I'm curious to see where this is going to go. At the heart of everything we see, touch, and experience are atoms, the fundamental units of matter. Shout out to the atoms. Each atom consists of a nucleus made of protons and neutrons, and surrounded by a cloud of electrons. These tiny structures come together in countless combinations to form molecules that make up everything from the air we breathe to the stars in the sky. Consider a single drop of water. It contains approximately 1.5 times 10... 1.5 times... I'm really not good at reading numbers. 10,011.5 over times 10 to the 21. 1.5 times 10 to the... Oh! 1.5 times 10 to the 21 times 1,021 water molecules. Okay, got it. Each made of 2 hydrogen atoms bonded to 1 oxygen atom. Despite their minuscule size, atoms are incredibly significant, forming the diverse tapestry of the material world. Particles beyond the atom. Delving deeper, we find that protons and neutrons are themselves composed of even smaller particles called quarks, held together by gluons. Oh my gosh, it's been so long since I've heard about this concept. So this is, and I also never really truly understood it properly. So I'm curious. I'm very curious. Electrons, quarks, and gluons are part of a family known as elementary particles, which, as far as we know, are not made of anything smaller. Okay, so the absolute smallest of all small things. Obviously, electrons are tiny. I always teach this to the kids that, you know, electrons are considered to weigh virtually nothing. Whereas, as far as relative atomic mass is concerned, or just relative masses in the periodic table, protons and neutrons have an equivalent weight of 1 each, whereas electrons is basically 0. It's basically nothing. So that makes sense. These particles interact through fundamental forces governing the behavior of matter and at the smallest scales. Understanding these interactions is key to unlocking the secrets of the universe. Do drop any comments you guys have in the comments section as well, about anything, because he did say I could ask him questions to share. So hey guys, throw your questions in there and we can find out, because we're all learning here, myself included. The fundamental force is simplified. There are 4 known fundamental forces in nature. So let's just recap this a second. Okay, so these particles interact through fundamental forces governing the behavior of matter at the smallest scales. Okay, okay, got it. Oh, okay. Gravity, what it does, attracts. So these are the fundamental forces talking about that take place between these elementary particles. I hope I'm saying that correctly. Elementary particles. Let me just make sure that I'm not talking about nothing. Yeah, elementary particles. So we've got gravity. We're talking about the fundamental forces. Gravity, what it does, attracts objects with mass toward one another everyday experience. I like this way of writing things out. Everyday experience keeps us grounded on earth. So we've got, for all of these, he's basically split it into what the thing does is everyday, how we experience it every day, and the unique feature of each individual force. And I like that he's include like the everyday experience, because I always say to people that science, and this is my problem with the education system, science isn't supposed to be something that you think about that's like separated from you. It's supposed to be a part of your everyday experience. So I feel like the education system is lacking, because we should be doing experiments that people can relate to as far as their actual lives. We should be looking at things as far as your actual genuine experience, much like how he's referenced air, and we breathe air, and we can look at the stars. Those are two things that you can actually do, how you interact with science. Also, so I like this. So gravity, what it does, attracts objects with mass toward one another. Everyday experience keeps us grounded on Earth, governs the motion of the planets and the stars. Unique feature, although it has an infinite range, gravity is the weakest of the forces at the particle level. That's very interesting. Okay. Electromagnetism. What it does, acts between electrically charged particles. Everyday experiences, powers electrical devices, enables magnets to stick to refrigerators. I like, again, the use of like ideas. He's really written this book for people that are not even scientists, to understand even the deep levels of science. So that's quite cool. Unique feature, responsible for light and all the electromagnetic radiation. And we have strong nuclear force, holds protons and neutrons together in the nucleus. That's actually such a good point, because now that I'm thinking about it, I never really thought about what was holding the protons and the neutrons together, because protons are positively charged and neutrons are neutral, so there's nothing to attract them to each other until now. Everyday experience, not directly felt but crucial for the stability of matter. Unique feature, the strongest force operates only at very short ranges within the nucleus. Okay, so this is within the nucleus. Weak nuclear force, what it does, responsible for radioactive decay and certain nuclear reactions. Everyday experience plays a role in processes that power the sun. Unique feature, affects subatomic particles and also has a short range. Okay. Fields, the invisible influence. So, a field is a region in space where a force has an effect. Okay. We're getting into it now. Like, this is a hot. You guys have no idea how much I love this. This is okay. This is so good. I love this. This is what I love. I love science, guys. I love it. Okay, let's get into it. Hold on. Just give me a second. Okay, so we're going into fields now. A field is a region in space where a force has an effect. Think of it as an invisible landscape that tells particles how to move. Okay. So we've got the gravitational field, determines how objects with a mass attract each other. We've got an electromagnetic field, governs how charged particles interact. Quantum fields, in quantum physics, every particle is associated with a field that permeates space. Okay, an easy way to visualize a field is to sprinkle iron filings around a magnet. The filings along the magnet's field lines. The filings align along the magnetic field lines, revealing otherwise invisible influence. That is true. And we used to do that experiment. Well, not the experiment, but that demonstration I've done before. Also, and this is why I love the thing about being a student of life. These are the types of things, when you're reading, I do the same exact thing with the Bible. Go and Google it and have a look at what that is. Like, you know what I mean? Go and search and study and visualize. I think visualization is a really important thing in science. Don't just read things. Go seek to understand. Like, when I didn't know what a tesseract was before. I went and saw a tesseract, and now in my mind I have a vision of what that kind of concept is. Waves and duality. Particles can exhibit both particle-like and wave-like properties. Here we go. A concept known as wave-particle duality. Light as a wave exhibits interference and diffraction patterns, right? Light as a particle, photons deliver energy in discrete packets. Electrons and other particles Also display wave-like behavior and demonstrate as demonstrated in the famous double slit experiment. I've never heard of that, so hold up. Okay, I think I understand. I'm gonna ask. Let me write this down. Maybe I should actually hold on. Okay, I'm gonna ask him. And I'm gonna get back to you about that, because I honestly feel like addressing that whole concept of waves and light and all of that is going to be important for us regardless. So even if I do that as like a bonus video explanation type of thing, we'll do that. So I'm going to ask him specifically. I get kind of the gist from what I can see. Like you have two slits, a light coming through, and then the interference pattern where there's a pattern of how exactly the light hits certain spots, and there's certain spots it hits more than others. And I can kind of see that the waves come down to these certain spots for whatever reason I don't understand. So I'm going to ask him. Let's continue. The uncertainty principle. Oh, it's been a long time. At quantum scales, the exact position and momentum of a particle cannot be simultaneously known. This is what I'm saying. Right? This uncertainty isn't due to measurement flaws, but is inherent to nature. Implications leads to phenomena like quantum tunneling, where particles can pass through barriers they seemingly shouldn't be able to. Everyday analogy. Imagine trying to measure the exact speed and position of a hummingbird's wings mid-flap. It's not difficult, it's fundamentally uncertain at that scale. I love you see that you can actually make science approachable. You see what I'm telling you guys all the time? I'm telling you all the time that people, I honestly feel like it's done on purpose. That science is made so confusing. Okay, limitations of current models. While quantum mechanics and general relativity are highly successful in their respective domains, they are fundamentally incompatible when it comes to describing certain phenomena, such as what happens inside black holes or the conditions at the universe's inception. The need for unification. Physicists seek a theory of quantum gravity that would reconcile these two pillars of physics. Those are two extremes. String theory and beyond. I can't believe we're at string theory. Proposals involving extra dimensions aim to bridge the gap. I see. So we're looking at the fact that the reason maybe we don't understand what's happening inside black holes or the conditions of the universe's inception could be that we're still going back to, an example that he mentioned earlier in the book. We're looking at things, maybe the reason we're lacking in understanding is we're not understanding that there are other dimensions that explain more. So, for example, the very good example he gave of like, if you have a cube or even a sphere, the shadow of that sphere or cube, which are 3D shapes, is going to be 2D, right? You've got a sphere, you're going to see a circle. If you've got a cube, you're going to see a square. Obviously, square being two-dimensional, cube being three-dimensional, etc. So perhaps some of the things that we're seeing, again, based on the fact that we know we're in the third dimension as well, essentially, maybe the reason we're not understanding is because we're seeing like a shadow, and the shadow isn't giving understanding to whatever this actual thing is in that sense. And so hence why scientists are studying into the dimensions. It's also why I'm curious about the dimensions as well, because it's like, well, what is it that's next? If that makes sense. What could it be? And maybe it's because we haven't considered that we don't understand some of these phenomena, such as black holes and the universe's inception. Opening the door to new ideas. Understanding the building blocks of the universe sets the stage for exploring theories that push the boundaries of conventional physics. The bubble theory is one such idea, proposing that additional dimensions and structures could provide answers to unresolved questions. As we continue our journey, we'll build up this foundation to explore how the bubble theory might integrate with or extend these fundamental concepts, offering new perspectives on the nature of reality. So just again, I'd like to highlight, this is one of the reasons why I way prefer to read this than say like just a random book. And the reason for that is, you see how with these types of texts, you are brought through the journey of where we started, what is the foundational like information you need to know about this topic. Then you add layers and layers and layers to build into whatever your theory is. That's, in my humble opinion, the best way to go about learning things in life. Don't just take what people say for granted, and don't just go with whatever you're told all the time. Stop and have a critical thinking, because along the way so far we haven't even got to, he's mentioned a couple of times the bubble theory and kind of what it's going to be, but for the most part he's building up a foundation for us to understand exactly what is it that goes behind this theory, right? And that's what I think makes good proper scientists, is you do that. You don't just tell people you need to believe this and this is what it is. It's like, well, this is how I got here. And that's what makes science competitive, because people are going to look at your work and they are going to critique it, because they're going to say, well, how did you come up with that? As I told you, you have to take them on the full journey. Even when I did my own research paper, honestly, the introduction was the hardest part. Because I have to explain what's computational chemistry, what is how where have I figured all these things out. I've got to break down the basics. And also, if you are doing your due diligence as a scientist and as a person, so I said these are skills in life that you can use for your own benefit. Your ability to be able to know why you're saying something and to explain how you got there is a huge advantage, because then you know yourself that what you think, you have good reason to be thinking it, and you're not just pulling something out of the air. So I quite like that quite a lot. Now we are he's got his key takeaways, his summaries. So atoms and particles. Matter is composed of atoms, which consist of smaller particles like protons, neutrons, and electrons. Fundamental forces. Four forces govern interactions in the universe: gravity, electromagnetism. Why can I not say that? Electromagnetism. Strong nuclear force and weak nuclear force. Fields and waves. Fields influence how particles move, and particles exhibit both wave-like and particle-like properties. Quantum mechanics, which you guys know is one of my absolute favorites, introduces principles like wave-particle duality and uncertainty, revealing the complex nature of the microscopic world. And finally, challenges in physics. Current models have limitations, highlighting the need for new theories that can unify our understanding. So all to say, and I'll finish off this with saying, we're going on to dark matter and dark energy next. It's going to be so good. All to say that, just another proof that, science is very much still on its way and still working a lot of things out. There's a lot of things we really don't know about yet. So that's what I think is the fun of it as well. I think it's fun to be alive in a time where we have so much access to information. There's things that haven't been figured out. There could be, who knows when there's going to be the next huge scientific breakthrough. It could be literally any minute. And this is why these things are so fascinating, I feel. But yeah, so you guys, let me know your thoughts in the comment section down below. Let me know if you guys are enjoying this, because I'm actually having a whale of a time. This is me nerding out to the oblivion, because this is my kind of text to read, because it's engaging my brain. It's above what my current understanding, so it's pushing me to also learn more, which is exactly the point. So as I said, I'm going to ask the question about the double slit experiment and maybe a couple of other things. And so yeah, just keep watching. If you've enjoyed this, there's a whole playlist. I'm aiming to do one video a day, of one chapter, or so. Also to give us time to debrief. Like I said, everything's linked in the description box below. Go and check out the playlist for all the videos. Go and get the book as well if you'd like to get the book for yourself. I highly recommend. I think it's one of those that's worth having on your bookshelf. I told you I really be thinking about what books I want to have on my bookshelf. So yeah, other than that, you guys, if life's a game, let's play to win. God bless you all. God loves you. I love you. And I'll see you in my next one.